biological neuron can be divided in four main parts: the dendrites that receive signals from other neurons, the body of the cell that aggregates these signals, and the axon that sends signals generated by the body of the cell down to the axon terminals and to other neurons. A digital neuron has similar parts, has a very similar structure. Now, we don't typically represent a digital neuron like this. We represent it like this. And we often call them perceptrons. Now, the first part on the left-hand side of the diagram, those are the inputs. So that's the data going in the perceptron. Each of the values of these inputs are multiplied by a constant, the weights, and then the results are added together in what will be the equivalent of the cell's body. And then the result of this summation is transformed using an activation function. Now, I would like to bring your attention to this part of the diagram where if you look at the input, it's a constant value of 1. So in a sense, the signal that reaches the summation part is always going to be W0 there, a constant. And this is what we call the bias term. This is a trick that we have. Adding that constant input of 1, value input of 1, is the trick that we have to represent the bias term in a convenient way from the point of view of artificial neural networks. Each of the values there, x1, x2, etc., those are different features, okay? So they are not different samples. So these are different features. So if we want to, every time we want to fit a different sample to the perceptron, we need to pass a whole feature through the perceptron. Now, in terms of activation functions, there are many different ones. These are some of the most commonly used, although there are others. I would say the most interesting thing to note here is the plot and the range of each function. So the identity function basically doesn't do anything. What goes in comes out. The binary step equals 1 whenever the input is equal or greater to 0, and then it equals 0 otherwise. So for values lower than input values lower than 0. And then the logistic function is a smooth function between 0 and 1. So the interesting thing about the logistic is that it's very similar to, or the output that it produces is very similar to a probability, and therefore it's easy to interpret intuitively. And then the hyperbolic tangent that is similar to the logistic, but that ranges between -1 and 1. Now, to demystify the maths behind the perceptron, let's see what happens if we use a logistic activation function. So there in the slide, I have expanded set, that intermediate value set, so that it looks like W0 plus x1 times W1 plus x2 times W2, etc. And now if we set the value of the activation function to the logistic function, we get 1 divided by 1 plus the exponential of set. This is a logistic regression algorithm. So if we use the logistic activation function in the perceptron, we get an logistic regression algorithm. So there is nothing magical about the maths behind the perceptron. I guess the only difference, if you wish, you can see the perceptron as a logistic regression where where we have the liberty to change the linear combination of features to something else. Sorry, the non-linear part. Sorry, not the linear. The non-linear part where we of the logistic regression to something else. If we were to use the gradient descent to optimize the perceptron, which we usually do, we will we will fit the outcome of the output of the perceptron to a loss function together with the target, the desired output. And then the idea here is to find the arguments that minimize this loss, the values of the weights that minimize this loss function. From using the gradient descent, we know that what we need to do is to find the derivative of the loss with respect to the weights, to find this, to know how to modify these weights to minimize the loss. And by applying the chain rule of the derivative, we know that the derivative of the loss with respect to W equals the derivative of the loss with respect to the predicted value, y hat, times the derivative of the predicted value with respect to Z, times the derivative of Z with respect to W. So, in a sense, the derivative, it's almost like traveling backwards through the perceptron. So the derivative of the loss with respect to y hat is the representation of if the value at the point of the output. And then if we move this to the left of if we propagate this backwards through the activation function, we get now the derivative with respect to Z. And then if we move it backwards to the left of the summation, we get the derivative with respect to W. The issue with the perceptron is that it's but a linear classifier, the same as the logistic regression. So how do we improve the perceptron? Well, we use artificial neural networks, which is just a combination of perceptrons, really. We stack perceptrons one next to each other to create layers, and then we connect these layers one to the next one. So here the first layer is what we call the input layer, and this is just the data. And then the output layer, the last layer is what we call the output layer. And everything in between are called hidden layers. Hidden layers because as a user, you see the input because that's the data that you're feeding into the artificial neural network, and you see the output because that's the values that you get coming out of the artificial neural network, but you do not see typically what is in between. Now, when I say that each of these layers is connected to the next one, usually these are fully connected layers. So that means that each neuron in one layer is connected to all the neurons on the next layer. Although this is not necessarily always the case, but this is most typically the case. Now, bear with me as we go through the mathematics behind artificial neural networks. I know they are going to look like a lot, but I promise you it's just the same thing applied over and over and over again. Right, so each layer is defined by a weight matrix, W, and an activation function, F. So the weight matrix, W, it has dimensions number of inputs times number of outputs. The number of inputs for that layer is the number of features of the data going into that layer, and the number of outputs is just the number of neurons in that one layer. Okay? Now, because layers are connected in sequentially, then the input to the first hidden layer is what comes is the data. So we have the number of inputs is the number of features, and then that first hidden layer outputs as many values as number of neurons in the hidden layer, and that then is sent to the second hidden layer, and therefore the input of the second hidden layer is the output of the first hidden layer, which means that the number of inputs of the first hidden layer equals the number of outputs. Sorry, the number of inputs of the second hidden layer equals the number of outputs of the first hidden layer. And that's what we see here. Now, what's going on inside that? Each layer is exactly the same that goes on in the perceptron, but just multiple times, one time for each neuron in the hidden layer. So we have the same intermediate values set, and then we apply the activation function to that intermediate values. And as I said, it's the same intermediate values. They are just the product, the result of the summation of the products between the input features and each of the weights, okay? And again, we're just repeating this in parallel multiple times for each neuron in the hidden layer. Now we connect again the output to a loss function. And again, the idea is that we want to optimize, find the values of W that minimizes the loss function following the gradient descent algorithm. So what we do is we propagate this loss or the derivative back through the network. So that's why we call these networks, these artificial neural networks, back propagation. That's what we call this way of learning in artificial neural networks, back propagation. So here we can see that at the output, but propagating backwards of each layer, we have the derivative of the loss with respect to the output of that layer. So, for example, if we look at the hidden layer 2, we have at going in on its right-hand side, so on the output, but going in because it's propagating backwards, we have the derivative of the loss with respect to its output, H2. Now, these are the maths behind this. Again, these are exactly the same that we saw on the perceptron. It's just that it's written in matrix notation to denote that we have multiple neurons within each layer, but it's exactly the same chain rule of the derivatives that we saw on the perceptron. Exactly the same thing. Okay, so there is nothing new here, really. Now, see how the first calculation at the top is the derivative of the loss with respect to the weights, with respect to W, and this is what we need on our gradient descent algorithm, so to optimize the artificial neural network. And then the second part, what we are calculating is the derivative of the loss with respect to the input of each layer. Why so? Well, because this is what we are back propagating through the network. So each layer what it does is it moves, so to speak, it moves the derivative of the loss from its output backwards through its input. And then we send this to the previous layer, which does the same, and then send it to the previous layer, which does the same. This stops at layer 1 because it doesn't make any sense. It's not necessary to send this to the input layer because the input layer is just the data. There is nothing for us to do there. Now note that the only thing that is different between these two computations, the derivative of the loss with respect to the weights and the derivative of the loss with respect to the inputs, is just that last term on the chain rule. And then this can be simplified, this notation can be simplified. And again, the reason why I put this here is just to highlight that actually each layer is doing exactly the same thing. And within each layer, what's happening is that each neuron is doing exactly the same thing, which is what we saw on the perceptron. So again, I know that the mathematical notation may look like there is a lot going on here, but it's not really a lot in terms of complexity. It's just a lot in terms of quantity, but it's actually the same operations again and again and again, and these are just those. These are just the ones that we saw on the perceptron, which, as we established, it's nothing overly complicated because, in a sense, it's just like a logistic regression where we have the flexibility of changing the logistic function with any other function. So what are the configurations of the artificial neural networks? Well, in terms of hyperparameters, we need to decide the number of layers, the number of hidden layers that we are going to use for our network. We need to decide how many neurons we are going to have in each layer. Note that we don't necessarily need to have the same number of neurons across all the layers. We also need to specify what are the activation functions for each of these layers or for each of these neurons. Typically, all the neurons within one layer share the same activation function. And again, typically, we don't change the activation function within an artificial neural network. So across layers, they all have the same activation function, except perhaps at the output where we may want to do something else, like using the softmax function to try to obtain a normalized output that resembles a probability, meaning that all the values, each associated with a different class, they all add up to 1. And then we need to specify the learning rate when we use the gradient descent algorithm. And then in terms of parameters, we just need to find out the weights. Those are the parameters of our artificial neural networks. And again, if we use the gradient descent algorithm, we can find this out automatically going through this gradient descent algorithm or learning and doing backpropagation. Now, in artificial neural networks, there are many other things to consider, okay? So first, the learning algorithm that we are going to use. I just mentioned now the gradient descent, but that can be modified. There are many things that we can do to improve the gradient descent algorithm. We can add regularization to avoid overfitting. We can use momentum to try to speed the learning. We can apply Nesterov correction. We can use a learning rate decay so that we can start with a very large learning rate and then reduce this learning rate as we learn so that we don't overshoot the minima as we get closer to it, and many other alterations that we can use, or improvements or changes that we can do to the learning algorithm. Which ones we should use, again, it will depend on the data and the problem in hand. We need to decide also what loss or what error function we want to use, because this will also yield different results. And then we need to decide the architecture. So the artificial neural network that I presented is the typical fully connected feed-forward artificial neural network, but there are different architectures. You can skip connections between neurons, between one layer and the next one. You can skip layers and connect, for example, the input layer to the first hidden layer, but then also to the output layer directly, and then combine the input data with the output of the last hidden layer, for example. I mean, there are many different architectures within the field of artificial neural networks. And in fact, that's an advantage of artificial neural networks, which is that it's very, very, very flexible. There are many things that we can do with artificial neural networks within the context of artificial neural networks. And some of these changes are quite profound and will yield very different results. Artificial neural networks, generally speaking, are quite robust against noise, and they can build very complex models, very complex input-output models. And this is perhaps the most desired quality of artificial neural networks. However, they require a large amount of data to train well. They can be expensive to train, meaning that usually it takes quite a bit of time to properly train an artificial neural network. So not just data, but also computational time, going through that data again and again and again. And then perhaps the biggest drawback of artificial neural networks is the fact that the models they come up with, the input-output models that these algorithms produce, are fairly complex. They are complex, and generally speaking, they don't make much sense to us, in the sense that we cannot explain these models in human language in a way that is intelligible for us. That's not to say, that's why we call them black box. That is not to say that we don't know what's going on inside. As I said, it's just that the models are not easily interpretable. So if you think again, back to the case of what happens if we use logistic activation function, and then we say, well, that in the case of the perceptron, that is basically having a logistic regression algorithm. So in a sense, if then we move from perceptron to artificial neural networks, what we're doing is stacking logistic regressions together in a specific way. As you can imagine, that is not going to be very easy to interpret for us, or is not going to make much sense for us. It doesn't mean that the input-output model doesn't make sense or is not relevant. It's just that the way we mathematically model that input-output model is not doesn't make sense for us for us humans in our language, say.